Hi everyone, it's Ethan, Teacher's Math here, and today I'm going to be going through a connected particles question. I'm going to make it as easy as possible, and I hope you enjoy. Alright, let's get started. So here we have two particles, A and B, of mass m and 2m respectively. And after reading that, I'm just going to look at the picture and make sure I see what I'm reading. We're told that they're attached to the ends of a light inextensible string. So we'll go through what that means at the end. And we're told that the particle A lies in a rough horizontal table. Rough obviously means there's friction. The string passes over a small smooth pulley. Smooth meaning there's no friction. And we can see that on the edge of this table over there. The particle B hangs freely below the pulley as shown in the diagram. Perfect. And we're told what the coefficient of friction is between A and the table. It's mu. The particles are released from rest, blah 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 blah. Okay, we'll use that stuff later on, but immediately after release, the magnitude of A is this. Perfect. Okay. So one thing that I always tell all my students when doing connected particles question is you must treat the whole thing as one system. But by doing so, you can think of it as having a magnifying glass and being able to zoom in into each particle individually. So what does that mean? Well, imagine you have a magnifying glass and you hover it over particle A. So if you do that, you can see all the forces on A. It will have a force acting downwards, which is of course its weight, which is equal to mg. F equals ma, weight equals mass times gravity. And because A is pushing down on the table with force mg, due to Newton's third law, the table is going to push back up on A with an equal and opposite force, which is called the normal reaction force. It's called the normal reaction force because it's at 90 degrees to the surface. It's really important. For example, if you had an inclined plane, the normal reaction wouldn't be straight up. That would be wrong. It would be at 90 degrees to the surface. Just a little point there. We're also told there was friction. So I can draw in friction acting towards the left. And of course, friction is equal to mu r. One thing I just want to emphasize, how do we know friction is going to act towards the left? Well, if you look at both particles, A and B, what one's heavier? Well, you can clearly see A is mass m, B is mass 2m, B is heavier, therefore B is going to be traveling down and A is going to be traveling towards the right. And they're both going to have magnitude, which just means size, 4/9g. And same with B, because they're connected, they're both going to have the same acceleration, 4/9g. Okay, perfect. What else do we have? Of course we have a string. So if we have a string, that means we're going to have tension on the string. So going back to my magnifying analogy, I'm going to draw from the point of view of A. Imagine you are particle A. If you're particle A, there's going to be let's call it a magic force kind of pulling you towards the right. And because we're zoomed in, we don't know what that force is. And of course, if we zoom out, we know that force is from B. So that's why tension will act towards the right from A's point of view. Now we're going to zoom into particle B. We're going to have the tension acting upwards on B, because imagine your particle B, you're traveling downwards. Why are you traveling downwards? Well, because you're heavier than particle A, so when you're released from rest, you're going to pull A along, but you're not going to go down as fast as you can because there's someone trying to pull you back. You have some drag, and that drag is you're dragging A along the table, and we call that drag tension from B's point of view. Now, a lot of people get confused as to where the tension and direction of the tension should go, and you can just think of it as this. You need to look at it from the point of view of A and B. Imagine you are particle B. What forces do you feel? And that's how I like to think about it. So now we've got a really good force diagram. We can put some of the numbers in for part A. So part A wants us to find the tension, and okay, so part A and B is asking us to set up two equations. So let's start off with particle B, and you'll see why in a second. So of course we're going to use Newton's second law, F equals ma. That's the equation that we, 9 out of 10 times it's going to be F equals ma, and the other 1 out of 10 times it's going to be SUVAT for these type of questions. So F equals ma, we need to tell the examiner what way we're taking as positive. So we're going to resolve, in this case, downwards. So all that means is we're going to take the downwards direction as positive. So if you look at the diagram, look at B, what are the forces going downwards? Well, it's 2 mg, and that's positive. Why? Because we've told the examiner that we're taking the downwards direction as positive. What we're going to take away? Well, what are the forces acting upwards? Well, it's tension, T. And that's equal to the mass of this particle, which is 2m, and the acceleration, which the question told us way back over here was 4/9 g. But of course I had a great diagram, so it was all easy. Okay, so we need to rearrange this equation and get T by itself. So we get 2mg minus 8/9 mg is equal to T, and that means T is equal to, well, 2 is just, imagine that's 2/1, so that's equal to 18/9, take away over 9 is 10/9 mg. And that's just a mental math, adding takeaway fractions in my head. Nothing crazy going on there. Okay, so now let's look at particle A. So when I say for A, I mean we're looking at the forces for A. Why? Because in A-level mechanics, because it's connected particles, we can consider each particle individually because they're going to have the same tension and the same acceleration, because they're connected on a light, inextensible string. Okay, so again, we're going to use the same equation, Newton's second law, F equals ma. We're going to take the right direction as positive, and the reason why I'm taking the right direction as positive is because the particle is accelerating towards the right. So it just makes the numbers nicer. If I was resolving towards the left, it would mean my acceleration would be negative. It's still possible, but I just prefer to resolve to the right. In other words, resolve in the direction that the particle is accelerating. Okay, I hope that's clear. Next, so what are all the forces going towards the right? That's tension. What are all the forces acting towards the left? Well, that's friction, which by definition is equal to mu, which is the coefficient of friction, times r, which is the normal reaction force. And that's equal to its mass times the acceleration, which, I've already got on the diagram. It's 4/9 g. Okay, so then we have tension, which we already know. It's 10/9 mg minus mu. Now, we'll come back to r in a second, but that's equal to 4/9 mg. Okay, so how do you work out the normal reaction? To work out the normal reaction, you would resolve upwards, still for A, using the same formula, force equals mass times acceleration. So we're resolving vertically, so R minus mg is equal to ma. And of course we know A is 0. Why is A 0? Well, I don't know about you, but I don't think this particle is flying off the surface. It's going to stay on the surface. It'd be very strange if it just started flying away. So therefore R is going to equal mg. So I can replace R here with mg. Now I can divide both sides of the equation by mg. By doing so, I can cross out all the mg's. Then I can just do some basic algebra, rearrange for the coefficient of friction, which is mu, and I get mu is equal to 6/9 which, below and behold, surprise, surprise, is equal to 2/3. Okay, so that's part A done. I'll tick that off, and that's part B finished as well. It's the same for pretty much every question like this. You look at the particles individually to work this out. Now, a quick question that you might want to ask yourself, and you can leave in the comments below: why did I choose B? Why didn't I consider the particle A first? Okay, so that's what I want you to answer in the comments.